So yesterday we looked at how we differentiate trig. Now we want to know about going back the other way. Just dealing with linear functions to start off with here. If we integrate cos, well, we saw that when we differentiated sine, we got cos. So therefore, logically, when we integrate cos, we go back to sine. But because it's a linear function, we'll have 1 over that coefficient of x out the front as well. Now the sine one's where we've got to be careful, because we said when we differentiate cos, we got minus sine. So therefore, when we integrate sine, we'd go back to minus cos. So this now, we can make, well, how can I put it? It would be so easy to make a silly mistake, because you've got to remember when you differentiate cos, it goes to minus sine, but when you integrate sine, it goes to minus cos. Now, in exams, you will get a table of different formulae and what have you, and these basic ones are on there. So if you're ever unsure, you should be able to just, double check. And the third one we looked at, we said, well, when we differentiate tan, we get sec squared. Therefore, logically, when we integrate sec squared, we go back to tan. So there's the ones to start us off with. So, integral of sine. Well, sine will go to minus cos. Yes, it's a linear function, so I can just go minus a third cos 3x. Cos goes to positive sine. However, in this case, the coefficient of x is negative, so we'll end up with negative 1/5 sine 1 minus 5x. And let's do a sec squared. So half x, so 1 over a would be 2 to tan x on 2. Defter integrals. It's always radians. Now, it's obvious here that I'm dealing with radians because we see pi on 6 and pi on 2. We're used to seeing pi. Even if they were just numbers though, if that was 0 and 1, that's where you've got to be careful. It's radians is the angular measure. So whenever you're dealing with calculus and trig, radians is the circular measure that we're using. So we integrate sine, it'll go to minus cos, 1 over a minus a half. So substitute in pi on 2, we'll get cos of pi. Substitute in pi on 6, we get cos of pi on 3. And we'll see those numbers coming up a lot because obviously they're our exact values that we can substitute into. Cos of pi is negative 1, isn't it? Yes, curves down the bottom. And pi on 3, which is the same as 60 degrees, cos of 60 is a half. So minus 1, minus a half, we end up with 3/4 for our answer. Now, of course, with trig curves, you're going to have to be very careful. Are they asking for the integral, or are they asking for the area? Because remember, when it's below, it's negative, above, it's positive. Straight integrals are easy, we can substitute in. But obviously, trig curves are going to wind along the axis, and you're going to have above and below. So if it's area, be very careful. Let's do a volume question rather than an area question. The volume of the solid form when y equals the square root of sine pi x between x equals 0 and x equals 1 is rotated about the x-axis. You remember with volume, pi times the integral of y squared dx is the basic formula. So square root of sine pi x becomes just sine pi x, so sine of a linear function. So 1 over the coefficient of x, so 1 over pi, which will end up cancelling with the pi out the front. Sub in 1, we get cos pi, minus sub in 0, we get cos 0, and there we just get a nice neat answer of 2 units cubed. So all the same sorts of questions that we saw before with integration, but now we can use trig functions. Okay, that's great if it's a linear function. What happens if it's not? Similar to what we did with the exponential, I guess, is I want to create the derivative out front. Because I know if it says derivative times, well in this case, sec squared, then I'll just go to tan of the angle. The derivative of x squared is 2x. I only have 1x there. So let's set it up. It's now in the form I want to see. I've got derivative times sec squared times the function. So that'll just go to the tan of the function. So that's tan of x squared. So we've got a half tan x squared plus a constant. You'll find the vast majority of the questions they give us, they are linear functions, certainly at the 3 unit level. Extension 2, I guess we look at some more interesting ones. Yes, here's the question. This integral, you're going to see it a lot. Sine squared or cos squared, one of the two, or some multiple of it, or some multiple of x, because it relies on you using your double angle. Sine squared comes from the double angles. Cos 2 theta, one way we could write it was cos squared minus sine squared. Well, that's not very useful for what we're about to do. But I could write it as 1 minus 2 sine squared theta. When we make sine squared the subject, it becomes a half of 1 minus cos 2 theta. But we could also write it as 2 cos squared theta minus 1. If I make cos squared the subject, we get a half of 1 plus cos 2 theta. So they're very similar. Sine squared, it's minus cos 2 theta. Cos squared, it's plus cos 2 theta. But what it allows us to do is to integrate that sine squared, because I can get rid of the squared now and say, well, that's a half of 1 minus cos 2x. And now I've just got cos of a linear function. So the 1 integrates to just give x, and the cos goes to sine, but there's a negative there. 1 over the coefficient of x, so 1 over 2. And then a half of all that, so tidying that up, I've just multiplied out x on 2 minus a quarter sine 2x. But as I say, you will see that integral. I don't know that I've ever seen an HSC without it being in there somewhere, whether it's just a straight integrate sine squared or it's part of another question, but it's always there. Okay, back to this one, which appeared before, it should have before, but now it's here. Tan. How do we integrate tan? Now I gave you a bit of a hint of that yesterday when we were doing the derivatives, because you can rewrite tan, of course. Tan I can rewrite as sine on cos, and I now have a situation of derivative on function. Almost. Because of course the derivative of cos x is minus sine x. So I'd actually like minus sine x on top. To balance that out, I put minus out the front. I now have derivative on function, so that integrates to be the log of cos. So minus the log of cos. I think a neater way of writing that, so remember we have log laws which says the number out the front or the coefficient can come in as the power. Well, that power is negative 1. Cos to the power of negative 1. In other words, the reciprocal of cos is sec. I think that's neater because it's positive. That's just me. It doesn't really matter. I mean, minus the log of cos or the log of sec, both the same. What I am suggesting to you, and will probably happen, is you will end up memorising that. The reality is when I see integral of tan x, I just write down log of sec, because I know that's what it is. Okay? But if you do forget, then okay, this is where it comes from. The tan becomes sine on cos. In extension 2 integration, we actually do a whole heap of different trig integrals. That would, I guess, just be the start of it. So an extension 2 student certainly should be looking at tan and just know, oh yeah, that one goes to the log of sec. You don't waste time, I guess is what I'm saying. If you can remember these, and you should end up remembering the tan, you'll see it a lot, I think. You'll get the log of sec or minus the log of cos. Oh yeah. Okay, cos x times sine x to the power of 7. So what's happening here? Where did this come from? Remember, this is the answer to a derivative. What did we differentiate to get something like this? And it must have been sine to the power of something, because we would have brought down the power, lower the power, but then times the derivative of the inside. Well, the derivative of sine is cos, and we've got that there. So that's probably where it comes from. We could use that technique we saw of substitution, and we will see this technique again later this year, or later this term. And if I say, well, what's causing me the problem? The problem is probably the thing with the power. So if I let u equal sine x, then if I differentiate sine, I get cos. So I'll say, well, du is cos x dx. And I go back to my integral, I can see, okay, I've got cos x dx there, so I've got du, and then I've got u to the power of 7. And so all I'm doing is integrating u to the power of 7. But those limits on my integral refer to x. So I need to change those so they refer to u. And I can use the relationship we just wrote there. U is sine x. So when x equals 0, u is 0, x is pi on 2, u is sine of pi on 2, which is 1. And my integral becomes a very simple one of just u to the power of 7, add 1 to the power over the power, substitute in 1, substitute in 0, we get our answer. So again, that's probably a taste of what we'll be seeing later on. We'll see ones like that in the trig integral as well. There might be a couple in the exercise. Alrighty, I think that will do us for today.